Up to now, you have learned the electrostatic properties of the p-n junction. We have not applied any external voltage to it yet. In this section, you will learn what happens to the p-n junction when you apply a voltage to it. Before that, you have to learn how to calculate the carrier concentration at different locations of the p-n junction. In addition, you have to understand the driving forces that move the carriers. To begin with, let's draw the band diagram of a P plus N junction at thermal equilibrium before any voltage is applied. We will then draw the carrier concentrations at different locations of the diode in log scale because the values change over a few orders of magnitude and linear scale is not suitable. The concentration of holes on the P plus side is approximately equal to the doping concentration Na because holes are the majority carriers. We denote this by PP0. The first letter represents the carrier type, and P indicates hole concentration. The first subscript represents the region, and P means the P side. The second subscript, 0, represents at least the equilibrium value. The minority carriers or electrons on the P plus side is represented by NP0, which indicates the concentration of electrons on the P side at thermal equilibrium. If you remember, the product of P and N is equal to the square of Ni at thermal equilibrium, NP0 is just given by the square of Ni divided by PP0 or Na. Similarly, on the N side, the concentration of electrons is denoted by Nn0, which is approximately equal to Nd. And the concentration of holes is denoted by Pn0 and is given by the square of Ni divided by Nd. You should pay some attention to the relative magnitude of the carrier concentrations. In the graph, Pp0 is larger than Nn0 because it is a P plus N junction, with heavier doping on the P side. What about the depletion region? As shown in the band diagram, the number of carriers in the depletion region is not a constant with respect to position, and it is difficult to calculate, so they are usually ignored. That is, we do not care what is going on in the depletion region and simply ignore it by assuming that its width is very small compared with the neutral region. Please try to get familiar with these figures as they will be used very often in this section.